Okay, so it's a pleasure to introduce Alex, whose talk is From the Unforeseen to Foresight, Epidemic Modeling in the Age of Computing and AI. Thank you, Alex.
This should work. Can you hear me? Yeah, thank you. So thank you very much, Sally, for the very nice introduction. That's really a lot of things. Also, you embarrass me with all these things about knighthood, etc. So I will, this is a colloquium, so I will try to provide a general perspective on some of the research teams and science teams that are close to my heart, and I will not get into technical details. I'm very happy to dive into those or to discuss more. I know that we have some time together, and so after my talk, I'm happy to answer every question. So, as we said, my point is, okay, when we fight a pathogen, we are working with something that generally we don't see, especially at the early stage of an epidemic or pandemic. And I would say a lot has changed in the last 20 years in terms of the tools that we can unleash in order to view this invisible thing. Obviously there are many weapons, including all the work that is done in the front lines, healthcare providers at the biological level, all the advancement in genome sequencing, in understanding viruses, bacteria, pathogens, and then the vaccine and all the manufacturing that the pharmacological companies does to have weapons to contrast epidemics. But then there is one part that is the intelligence. So it's in a sense, what we do with modeling, with artificial intelligence, is to gather intelligence on what will be the next move of the pathogen, what will happen. If we achieve good insight on that, we can fight better our battle against a virus or a pathogen. When we talk about approaching this kind of work, I think it's very important to stress that I believe we are in an age in which is impossible not to use interdisciplinary approaches. And this is why I'm showing you this large number of people. Some of the people are really working in my team, some other faculty, other teams. This is because we need the all hands on deck approach in which we have to use expertise that goes from epidemiology and biology and genomic to the more advanced artificial intelligence and computing skills. And that's where we are, and this is why I have to thank many of the people that are in this image, because the work that I will show, it's not my work, it's a collective work. I think science is always a team sport, and this is what I will really show to you is because of many people contributing. Well, the first things is, and this is to get into the title of the talk, is that when we think about epidemic spreading, for sure we're talking about one of the prototypical complex systems that we have. In a sense, we have a lot of agents, a lot of interactions, a lot of different layers, network, contacts, transmission, traveling, commuting, etc., that generates effects and things which are not understandable if we look at the single components in isolation. And this is very important. This is what makes our life from time to time miserable in epidemic modeling, because if we don't accept those heterogeneities, those differences on the ground, then all our wishful thinking about intervention and doing things just fall apart. At the same time, you could say, well, if it's so complex, probably you can just have kind of theoretical understanding, conceptual understanding, but it's more difficult to get into something that is actionable. And I think here is the big lesson that we learned during the pandemic. We are called by society to do what I call actionable modeling. So otherwise we do not respond to something that is a need of the society. And during the pandemic, I think everybody, almost everybody, initially thought that we were at the same level of weather forecast, in which you can, get very nice maps, understanding what will happen tomorrow, what will be the best intervention. And I think we have proven during the pandemic that that was not the case. And this is where we have to work hard to achieve that. And I think this is where we are trying, and I mean not just me, my team, but the community, to advance quickly, to be in a different position with respect to where we were during the pandemic. Although during the pandemic, I think there is more success than probably many individuals realize. When we talk about this epidemic intelligence or epidemic modeling, I'm not talking about all the epidemic modeling. There is a lot of epidemic modeling that might be more retrospective, is understanding specific feature of transmission. There is a lot, is a very large field. I'm talking mostly about what I call outbreak analytics. This is really the intelligence, in the sense, the anticipation of the move of the pathogen. And so it means, first of all, monitoring and early warning, situational awareness. What does it mean? That, we want to know as soon as possible if there is something that is threatening us in terms of a pathogen, where it is, how many cases are out there, how is diffusing across the world. And these are generally things that are not easily accessible. Actually, you probably remember during COVID all the fog of what we say the initial part of the fight, because you get report from the fields, but whatever report is always with under ascertainment. We don't know the actual number of cases. We don't know the property of the disease induced by the pathogen, and so on and so forth. Then there is also, you want to go into what we call short-term forecasting and operation. You want to have something like weather forecasting, which you say, well, in the next 4 weeks, I'm pretty confident that this is what is going to happen. And around that, you build specific intervention, logistic, deployment of resources. Then you want to have the scenarios and counterfactual. These are what-if decision-making scenarios that might have much more long-range perspective, because at that point you want to build infrastructure, you want to decide what to do on the long term with social distancing, with schools, et cetera, et cetera. This is where you are not anymore in what we call forecast territory, but you are into something that is reasoning under assumption, okay? But you want to, in a sense, to provide an envelope or different trajectory for what could be the future. And then there is something also that is important that not everybody think about from time to time, is what we call heterogeneity inference. So in many cases, what happens in a pandemic is that is affecting different strata, geographical jurisdictions, sector of the population in very different ways. But we don't know that. We don't have the data that assess that level of disproportionate burden, unequal burden. And so in some cases, modeling is the only way that we can do inference on those features. So if we think about that, there are two things that we are used to work with, and this is coming from the modeling, from the mathematical epidemiology. We can use what we call mechanistic models. What does it mean, mechanistic models? This is something simple. Mechanistic model is a model in which you embed a mechanism for the transmission of the pathogen. This is the classic example that at this point after the pandemic everybody knows, the susceptible infected recover model. That is a toy model. No disease works like that, or at least it's very, it's really crude assumptions. But basically you have susceptible individuals, infectious, and then they recover after a certain time. And if you are infectious, you can infect susceptible individuals. If you describe the disease that way, you can imagine a population all of susceptible, introduce an infectious individual, and at this point, if you have the mechanism of the transmission, you can generate a mathematical form, constitutive equations for those mechanisms, and see how the infectious prevalence incidence will spread into the population, how many recover, how many infectious individuals, and you are able to describe the epidemics. And at that point, these open the grounds to make forecasts, to make scenario analysis, and so on and so forth. And these approaches generally can be as complex as you want. You can introduce more and more details. The simplest one, generally you have an explicit mathematical formulation. Here you see one. I don't want to get into the equation. This is just to say that you can write math, and this actually is a stochastic math in which you have a stochastic process that describes the evolution of the epidemics. And you know, through these processes, you have an understanding of the disease, and you have a mathematical formulation that you can solve if you're very lucky, and understand what is the dynamics of the disease. In many cases, this process has become explicit, but so complex to treat that you cannot do pen and pencil, and so then you need a computer to work with them. And the more they are complex, and the more you need big computer, big muscles, and in some cases, at a certain point, you also start to lose your understanding. You see effects that might not be completely intuitive. What are the common limitations, especially in the past, of those approaches? The first one is that they generally work in retrospective way. So you get the data, then you have a model, you feed the model, a lot of statistical theory behind it, you can describe what happened, but you know, in a sense, it explains what was already happened. It's more difficult to project ahead. In many cases, because the data were not there, and this is the second and the third bullet points, you don't have enough, you have to limit yourself to simple mechanism, to kind of toy description of what it is. When I'm thinking about an SIR, why I say that is a bit of a toy model, because no disease infect right away an individual. There is also always an exposure time. There is a pre-infectious time. There is a viral load in the body that grows and reach a peak and then goes down. And so all that is not generally in those models. And if you start to add those features, you need a lot of data that generally have not been available for a long time. The more the model is abstract, and the more perhaps is conceptually powerful, but is less useless for decisions. And so you have a trade-off. What happened in the last 20 years, and why I say that this is in the past? I say that this is in the past because in the last 20 years, something important happened in this scientific landscape. First of all, computational power. You know, the Moore's law, every 2 years, the computing power doubles, is there. And so in 20 years, it's a lot of computer power. I just had the memory, I was talking with somebody that you were mentioning, actually Sally was mentioning before punch card, etc. But when I was a student, at a certain point, we had a mainframe for the whole university. It was something that we were signing ourselves up to go in the night and work with this computer for an hour or 2 hours, something like that. And when we were working on, probably we were 100 people at once working on this computer. This computer probably had less power than one iPhone of several generations ago, the entire mainframe. So this is just to understand what computational power means. Data availability. Now we are digitalizing everything. We can acquire novel digital data streams. Our mobile phone, our mobile devices, our traces on the web, our traces on social network, etc. They are not meant to be public health data, but can be turned in powerful public health data. And then artificial intelligence and machine learning that have changed a lot and will change a lot what it's doing. And if we think about machine and artificial intelligence, we can go back to 2008, 2009. Perhaps some of you, with enough gray hairs, remember an article by Chris Henderson, I think, that was the editor-in-chief of Wired magazine. The article was called The End of Theory. And he was saying, at this point, we are collecting so much data that we can just throw into some machine learning algorithm and getting only answers. And we don't need to understand. We don't need to have a theory. I don't care. I have the answers. And he was also closing the article with, it's time that science learns from Google. It was not very well, how to say, it was not welcomed in the scientific environment, but obviously there were a few visionary points, because somehow you will see in a short, we are going in that direction anyway, but the poster child of that article, in a sense, was Google Flu Trend. Who knows what Google Flu Trend is? A few here, yep. Okay, a lot of you don't know. Basically, you have to know that to monitor the flu season in the United States, there is a very complex sentinel doctor system. The CDC is collecting data for what they are calling influenza-like illnesses visit, outpatient visits, hospital visits. We get hospitalization, but then all these data have to be collected nationally, are not the actual data is representative. They have to be statistically reweighted, et cetera, and then you get what is the flu activity in the United States. The issue is that every time you get the data point of 2 weeks ago, so in a sense you are always 2 weeks late, and you don't project. And then Google had a very simple idea. Why you do that? There are millions of people every day searching on Google. I extract all the searches which have cough, fever, I'm sick like a dog, I'm going to see the doctor, et cetera, et cetera. I take those searches, normalized by the whole searches in the population, and then obviously I need to, how to say, to crunch those numbers in an artificial intelligence. At that time was machine learning that calibrate those data with respect to the historical data of the CDC, so that I know how to rescale those numbers, and then I have right away, in real time, the flu activity. The idea was exactly that. At that point, you don't know why you have that activity. You don't know if it's because the strain has changed, because it's more transmissible, if there is less vaccination in the population. But you don't care. You get those things in real time. The system was working very well initially. Then he had the first problem when the H1N1 pandemic, a flu pandemic, hit in 2009, because people were searching pandemic because they were curious about the news and not because they were sick. They adjusted for that. And then, however, the system every now and then was, how to say, doing something wrong. So generally was right, but then at a certain point it might be 100% wrong. And that, the problem is that it was very unclear what was the problem. This is, for instance, is because one of the hypotheses was that those tools are alive. We don't search in the same way on Google every day. We change our behavior. For instance, Google at a certain point started to suggest what you have to ask. This changed completely the data. All the calibration that you have done falls apart. But this is, those algorithms are alive. They change day by day. There are obviously changes every minute in those big infrastructure. And so, at a certain point, the Google Flu Trend was abandoned a few years ago. This is not to say that Google Flu Trend is not a great idea. And actually now there is much better data that we can get with the same, in a sense, with the same strategy, in which you don't just use Google Flu Trend. You use many other proxy signals. They are called like that. For instance, reservation on OpenTable are a proxy signal. The the last minute cancellation on open table correlate pretty well with the flu season, as you can imagine. And so but if you put more proxy signal, more things to stabilize the system, etc., and then you use also other models, you can get good things. So this was a great idea, but it shows how many possible pitfalls we have in the system. And now the narrative in the last 10 years has changed from the big data to the artificial intelligence narrative. So it's not more the focus on the big data, but it's more the focus on the algorithms. Actually, nothing has changed because the big algorithms that are working now are working because we have the big data that they use to learn. So it's still the same stuff. And still, we have the problem of the black box, so that we don't know exactly what happens inside those algorithms. Well, here I have to do the advocate, to be the advocate for computer scientists. In some cases, they will tell you, hey, who cares? And they have some philosophical points. So if I ask you, what do you do when you have to teach your kid or friend to ride a bicycle? What do you do? So I'm a physicist. I could answer, well, I go to the blackboard and I start to the equation of the neutrons, then the torque, then the momentum, etc., etc. Will you do that? I'm a physicist and I won't do it. They are very complex equations, by the way. Will you do that? No. When the very young, when you will have a kid, you will take the kid, I did with mine, put on the bicycle, find a slope, and just push. And then hope that they don't kill themselves. And what you do is that you do those, you shout those counterintuitive things like faster, faster. No, because you know that if you slow down with the bicycle, you just, fall on a side. Because we know that you have to keep the momentum going. So why all that? This is to tell you that actually we have, humans have much more knowledge than what we can explain. So you know how to ride a bike, but you don't know how to explain to ride a bike. This is called tacit knowledge and has been put forward by Polanyi, who is a philosopher. And in a sense, many people are now saying, well, artificial intelligence is like that. They understand why they answer you in a certain way. They just don't know how to tell you. There is a kind of tacit knowledge. We are not able to understand their latent representation of the world in their parameters. And so, well, we don't understand, but they know. And it's not that simple. But anyway, we need to keep that in check, in the sense that there is a number of potential pitfalls when you use artificial intelligence algorithm. The first one is this black box, because anyway, we want more than the tacit knowledge. We want to understand. Second, the machine learns on data, and data can be biased. It depends. This is what we teach the machine. And so that's a big thing. Another thing that is always used in artificial intelligence is that more data, more knowledge, better results. In the health sciences, if I give a machine a time series of the flu from the 1900 to now, the machine is not learning good things, because in the 1900, it was a different healthcare system. We didn't know the antibiotics. We didn't know actually what was the transmission mechanism. So we are looking at different worlds. And so actually you have also to be very careful on the way that what is the data set time span that you pass to the machine. The other thing is that there are some actually deep mathematical reasons. Is rooted in the Poincaré recurrence theorem. When you have a high-dimensional system and you want an answer projecting in a low-dimensional system, because the projection will be only the number of cases of the flu, but actually the dimension of the dynamical system is very high, then if you pick up the wrong dimensional reduction, you will end up in being wrong sooner or later. So, there are things like that that are very complex and should be carefully considered. So what is my point? Is that we need to bridge a divide, one that is, epidemiologists, which have also strong component of social science in mind. So, they want to have causative mechanism, explanation, etc. Computer scientists, they want just to have something that answer and possibly answer, no, and actually answer correctly, but without all the mechanism behind. So we have to bridge this divide. And actually, my point is that in the last 15, 20 years, this is what's happening. So we are trying to go from, the simple time series to something that is much closer to what we do with weather forecast, where we have geography, we have dynamics, we have time information, we have explanatory power. Although even weather forecast, there is machine learning, even weather forecasts are computational models that cannot be solved by pen and pencil, et cetera, et cetera. But we know enough of the physics to read through the approaches that we use. And so we don't care, and what we did try to do, we as well as other groups, is to, try to keep open the interpretability of what is done, to use data science and artificial intelligence, but in a way that is compatible with all our mechanistic understanding, so that we can get better also all the things related to the initial conditions, what are the approximation that we get, what is the uncertainty that we get in our answer. So here I will show you a little bit what we are doing more generally. And this is something that it took 15 years in more than 15 years in the work. So we wanted to build a very large numerical simulator, and this is having the weather forecast in mind, of how epidemics spread across the world. So what we did is, first of all, what is the world? And the world for us is what we call a meta-population collection. So is many different subpopulations centered around the major urban areas or transport nodes, etc., which contain part of the population of the world. Each of the geographical area can be more or less dense. We do what is called a Voronoi tessellation. Some areas you will see there are no cells, let's call it that way. And this is because nobody is there generally, or in some cases really we have very little knowledge of the few individuals there. And so you, in a sense, however, they are not really relevant to the major mechanism. And this is, for each of those subpopulation cells, we collect how many people are there, the demographic, age structure, income, workplaces, et cetera, all this information that could be useful for the modeling. Then there are many networks that connect those places. The commuting pattern, the mobility pattern, and so on and so forth. So the first network that is crucial in this description is the network across single individuals. So that invisible fabric of the society that are our contacts. In this moment, we are having a contact that is viable for respiratory viruses. I'm talking, you are sneezing, you are breathing, and so we are all a complete graph that is connected. Well, in general, what we do is that you can think of that like you see here you have people in their households, and then they go to the school place, the workplace, et cetera, et cetera. You can generate theoretically this bipartite graph of people and location, how much time they spend in each location, if at the same time. And then if you do the unipartite projection of those networks, you can create those multi-layer networks for different settings in which individuals are in contact because they spend some time together. This you can do in a very data-driven perspective if you have, for instance, mobile data, which are very precise, or you can do through census data and so on and so forth. From the theory to the reality is a big jump. This is a real network, is a reconstruction from real data, and as you see, is much, much more complex than that simple vision. And indeed, to achieve this construction, you start from the microcensus data, which are classifying hundreds of thousands of families with all the attributes of those people, then you resample them and you create in each region of the world that you can control this way demographic curves that match the census data, like how many individuals in the household, what is the age in the individuals in the households, the age structure of the whole population. And from there, you basically generate a synthetic population that is not identical to the actual one, but is statistically equivalent to the actual one, where you really have individuals and their connection in the different settings. This is often numerically impossible to crunch for more than, let's say, 1 million, 2 million individuals. And in general, we use what we call mesoscopic description. For instance, you group by age, and you create contact matrices by age. That is a classic theoretical instrument of mathematical epidemiology. But you can also do contact matrices by income, by gender, by education level, and so on and so forth. Depending on the problem, it might be different. And there are several approaches that did those constructions at the worldwide level from census. And then the point is that we mount on those data a mathematical model of the disease diffusion. Well, this is one thing, but we want also to have not just synthetic construction, we want also to have data. For instance, there is a very famous study that is called Polymod, that's been done in Europe for several countries in Europe, in which there have been survey asking people who you have met, how many contacts, and so on and so forth. For instance, we are working now for the first representative survey in the United States, and the data will be available to the community, I think, in the next couple of weeks. We did already 2 waves. And this is really to create a ground truth of what is the contact pattern, for instance, in the US in the post-pandemic era, because actually contact patterns have changed after the pandemic. This is to have something that is really grounded on actual data. Well, always keep in mind when people tell you about ground truth, that is ground truth. If I ask you to record all your contacts the past week, it's very likely that you will not remember everything, etc. So there are uncertainties too, but you want to compare the different approaches so that you have a vision of the population. Then there is the mobility, because we are not just sitting in one place or going always to the same places. We do many other things, and we are very mobile. This is, for instance, is the state of Maine. This is a zoom in on the city of Portland in Maine. We work with agencies and the healthcare system in Maine. And you see the little yellow light are individuals. And you can really go at the level of single, you see Whole Foods is a market, Hannaford is another market, a restaurant, and so on and so forth. So you see, you can really map how people move around and how they are collocated. And so we use that information to have more data at the level of the single individuals. Then we have longer commuting patterns regimes. For instance, in the United States, there is appreciable commuting daily up to 50 miles. Is a lot, but is there. So you see, this is the commuting patterns in the United States that you can measure across counties. And then in the world, obviously, you can zoom in into those links that actually you can zoom in and get all those intricate patterns. And then there is another layer that is the one by the long-range mobility, airline travel, domestic, international, and so on and so forth. Those are data that 20 years ago were not available in digital form readily. Now we have in real time to those databases to know all the origin, destination, ticketing, stopover, etc. of the people. You put all together, and then you create really a big mechanistic model at this point. Because at this point, you can look at individuals like those susceptible, infectious, hospitalized. You can give all the attributes. You can provide age, you can provide sex, you can provide whatever. And then you have mobility flows connecting all those little cells on the world map through data. through actual movement data. This is the aim. And then there is a model that describes what happens when individuals are in contact. This is the natural history, for instance, of COVID. You see there are different kinds of infectious. There are latent, there are asymptomatic infectious, pre-symptomatic infectious, et cetera, until the hospitalization, the ICU, the recovered individuals, the dead, and so on and so forth. So you can enrich those models and make them as complex as you want. And these are called reaction diffusion systems because it's basically a large simulation of what's happening in the world. There is artificial intelligence here or not? Actually, there is a lot of artificial intelligence. First of all, in the movement inference, but then also in the population. When we are looking at those maps of the population, where the people are, they are not just a map that comes from a census data. That actually are maps that are a convolution through artificial intelligence of light emission captured by satellite, census data, information from other provider of mobile devices. So you see that you use those algorithms to produce data that then are used in a mechanistic model. And also you can use those mechanistic model in a flexible way because in some cases you may be interested to the entire world. In other cases you may be interested to a specific urban area and you don't want to use always, you don't want an overkill. So if you will use those networks and the detailed modeling you will be perhaps using for a specific city. While if you work at the level of the world, you may use more, how to say, coarse-grained things where individuals are not described exactly. This is, for instance, is one realization on a hypothetical epidemic starting from Boston. You see those white dots. These are single individuals traveling on an airline connection and going from one place to another where they can seed an epidemic, and then from those places other people travel. So you see, this is to give you an idea of the level of details that you can reach with those simulations. Now, what you should realize, however, is that this single realization is dominated by stochastic effects. So there is a lot of stochasticity. So you don't need one simulation. You need millions of simulations and then extract the statistical patterns. Those are the movement, and here you still continue to see movement, but at the same time you see also here, the epidemics that goes on. You have also epidemiological information. The more is red, and the more is the number of infected people. So you can combine all those layers and get different information that goes from the first people that gets to infect a specific place to how the epidemics evolve in those places. Well, when you do this, let me say that when you generate millions of simulations, one problem is to calibrate the model. So which are the simulations that are, and what are the parameters concerning the disease that really represent what we are seeing on the ground? To do that, I don't want to go too much in details, but there is an issue that is also classic in weather forecast, the fact that we have always uncertainties. Even when we were working with COVID, we didn't know the exact initial condition, the exact day of the first case, how much is transmissible the disease. We have always prior distribution, we say, some information that is a statistical information. And so we have to try for that space of parameters, then see what is the outcome of the different simulation, look at the data that we have, and then just select those trajectories that are close enough to the data. Those trajectories will define what we call posterior. So what is the probability that after the event, the data of the event that describe my system. When I have those, then I have confidence interval, and then I can also project in the future and see what's going on. The problem of the million of simulation, in a nutshell, is that you have to run 20,000, 30,000 computers at once, generate all those data. All those data is a big chunk of data that needs to be analyzed with supercomputing properties on high performance databases. And so it's a quite important numerical effort. This is where computer science is crucial. And for instance, during the pandemic, we were working on GP6 or Google Computing, I'm not doing advertisement, is because they really were generous and they gave us unlimited access to their machines. So that was, otherwise we wouldn't have been possible. Well, here again, artificial intelligence can be crucial. This one is a little bit the frontier. So what we do now is to try to bypass those numerical limits by using what we call surrogate model. What we do, we generate a subset of those trajectory of epidemics with the actual mechanistic model. And then we pass the information of the parameters that we use and the trajectory to an artificial intelligence algorithm. You see, who is a computer scientist here knows encoder, decoder, interactive neural processes, etc. What does the artificial intelligence algorithms? It generates a latent representation of the mechanistic model in the parameter space, and then is able to generate the trajectory automatically without executing the simulation, but just because he has learned what should be the shape given the set of parameters. Well, it's much, much more complicated than that. There are a lot of caveats, there are a lot of tests, and we are still working on all that part. But for instance, those curves are the correlation between the surrogate model and the actual model. And you see, these are very, 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 very good. In a sense, you get model that even if they are not completely fine-tuned, we are still working on it, reproduce what the actual model would give you, but 200, 400, up to 1,000 times faster. And that's projecting us into a new era for the future. What do you do with that? Well, when you have that, you can do things that, for instance, are looking at what we call the cryptic phase of an epidemic. So if you remember, if your mind, you go back to the pandemic, you remember that in February, everything seems quiet, but obviously instead the epidemic was brewing in many places, etc. So when did actually the pandemic got into the United States or other countries? Well, we were able to do those analyses, and it tells you that in California, actually the pandemic, this distribution gives you that the probability that there was already local transmission at a certain point in time. And you see that in California, basically, the largest probability is for the end of January. That is basically the same dates that we knew for the first time of the outbreak in Wuhan. And also you can look at how is the worldwide dispersion network. So this is the number of cases that of introduction in each state in the US in time. And you see that China is the red flow that actually is very tiny, because then we close traffic with China. But then the cases were coming from other places. And then in the whole United States, most of the introduction of the virus in specific places are domestic, were already domestic. Then you can do analysis on why we see different patterns in the United States geographically. You see, we go into the weather forecasting business in a sense. We can look at differences that depends on how many people travel in each state, what are the level of urbanizations, et cetera, et cetera. And the data can be compared, for instance, with the genomic data. All these analysis is for us one specific variant of SARS-CoV-2 that was the B117. And the data, as you see, are pretty good. Then when they breaks down is because actually that variant was not, at that point, was not the only emerging variant. There were others. So a lot of work can be done. And at a certain point, we land on the scenario modeling and forecast. We want to go to that question of saying, OK, what happens in the next 4 weeks? You see, you can calibrate the model on a certain number of data. And the white circles are data which, we say are out of sample data. So we don't use for calibrating the model, but were part of the scenario. These trajectories that are very different are the single stochastic realization that the model will give you, that you can treat stochastically to get your confidence interval, etc. Well, this is a science, but And at this point also it's important to stress that there is really rigorous methods to say, are things working or not? We have numbers in which these are all the models that runs, the CDC runs and contributes and does with us and many other actors, many other teams. And for each of them, you can say what was the performance with respect to a baseline model that is used as a baseline, et cetera, et cetera. So really, now there is something that is a benchmark. We cannot just say, oh, my model is better or worse, because we really need to compare across the board. And then we need to realize immediately one thing, that models are not oracles. So one model is always a model, and I'm sure you all heard, all models are wrong, some are useful. What is the point? The point is that this is state-of-the-art weather forecast for hurricanes. This is in the Pacific. Each of these spaghetti is one different model. And you see, they are all over the places. And you say, what do I do with this information? Actually, there is also one that is going inward. What do you do? And this is like for epidemic model. You put all together, they are very different. They give you different trajectory. They, close to the initial condition, they will be very similar. But then, they diverge. The issue is that we don't do that. We do this. Math is not just math, it's also communication. There is a consensus, there is a mathematical, there is a conceptual consensus, there is a process that has been done, and this is what we want to communicate instead of going with the single individual models. This is what we did with the Center for Disease Control, both for scenario forecast and for forecast and for scenario projections, with many, many other teams, and it's a work that is painful. It's, in a sense, is very different from the usual academic work, but is what we wanna do. Okay, need to rush. Forecasting, yes, there's a long way to go. The model has just 40% better of baseline models so far. It's something that in weather forecast took 50 years to build, where we are now. So this is where we have to work. Scenario modeling, it's even more work, in a sense that we need to understand better how even evaluate the performance of a scenario, because in a scenario there is no assumption that will ever be equal to the reality. And so how we compare if a model was right or wrong? There are many, many things. And so, but this is something where we need to continue working and offer our expertise, and 1 percentage point at a time. The other things that I want to show you, and this is really in the last 5 minutes, is how actually in some cases complexity can be used to our advantage. And this is some work that we did very recently in the last couple of years. So if you think about pandemic and epidemics, you know that always there is a cycle on newspaper. We should close airports. We should limit travel. We should measure the temperature of people at the gate, et cetera, et cetera. And those things generally do not work. And there are many reasons why they do not work, and so on and so forth. You see, there is a symptomatic and undetected transmission. The global mobility is all connected. It goes from one place to another. So, you're always in a kind of merry chase with the pathogen. You are closing Germany, and then the virus is in London, where you are still open, and so on and so forth. And then there is the political, social, and economic cost of this process. And so, at a certain point, some people had a very brilliant idea and say, well, the infected person jump on the plane. But then on the plane, at a certain point, they have to go to the bathroom. And so they infect the plane. No, they don't infect the plane, but they leave a trace of the pathogen in the wastewater of the plane. At that point, we can go, collect the wastewater from the aircraft, do the analysis, and look at the introduction of the pathogen. And this can be done in a passive way without requiring people to go through screening, etc. So this is, and we can set up a system to do that. Now, this is possible to do with analysis, with the testing, etc., etc. The problem is that now the mathematics, the intelligence, the analytics will tell you what is the sentinel system that we should build. How many sentinels we do have in the world to acquire a certain capacity. And you can do, with the model that I've shown to you, we can use the mechanistic representation. People are traveling, go, commute, takes on a plane. If they are in the detectable stage, that is the infectious or after the infection, if they're still shedding the virus, if they land in a specific place, you can detect through wastewater at the airport. At that point, they create a sentinel system in real time in the world. What is the point? I will spare you all the pain. You have to, in the model, introduce things. What is the probability that a person goes to the bathroom if the flight is 2 hours long, 4 hours long, 6 hours long? If you have the flu, you're also blowing your nose, and this is stuff that goes into the wastewater. So there are many, many things. Now, I don't want to go into the details. I'm really in the gory details and disgusting details. But now there are all those things, those numbers, and it's generally domestic. The detection probability is small because the flights are shorter and for other reasons. International, the detection probability is actually probably larger than 15% for any shedder, for a person that could potentially shed virus, 16 to 20%. And so we can do simulations and analytics with our system to say, what is the optimal sentinel system? And what is the targets? What is the time to first detection of this pathogen in the world? Can we localize the source? What is the outbreak at the source? How many individuals have been disseminated? And so we did this work. You can do by numerical simulations. And you see here with this color is the time to detection for an epidemic originating from those little cells. All the statistical treatment in which you see what is generally the distribution, because these are stochastic events. So in some cases you will detect after 5 days, in another case after 7 days, and so on and so forth. But you see that they have very well computable distributions that will tell you this is for a pathogen like SARS-CoV-2, and this is actually the full distribution of the median time across the world. It's about for SARS-CoV-2 of this reproductive number that was around 1.82, it's about 3 weeks, and this is really a short time for many reasons, because this is from the origin case. But there is a very good news that the model is telling you, and is this one, that 20 to 30 sentinel achieve 80% of 90% of the detection effectiveness of a system where we check in all airports in the world. So basically, it's completely useless to have more than 20, 30 sentinels. If we pick up the right airports, we are good. And actually, you have diminishing return after that. And this is one configuration, but the good thing is also that you can optimize the network in an adaptive way. So at a certain point, you know that the epidemics is from a certain region. Then I optimize the network for the detection with respect to that region. And it's also important, and this is the other good news, that a pathogen can spread faster or slower depending on several attributes of the disease, the generation time, the serial interval, things, technical things. But this time of detection always depends on the fact that you have a certain number of people that are carrying the virus or the pathogen traveling through the network. And this is between 20 to 80 individuals that diffuse around the world on average. And this is a very small numbers, because not all individuals that have diffused will start a chain of transmission. Some of them were already in the post-infectious phases. So you have detection at a moment in which there are still very limited outbreaks out there. And that's very important because it's the key crucial feature that indeed we can use not only for the first time of detection. So this is a case in which you see the first detection is in JFK. So the first detection was, after 31 days in JFK. But then I can continue to collect more detections and then use those as a kind of radar to triangulate where the epidemic is originating and what are the properties of the epidemic. Transmissibility, date of starting of the outbreaks. Obviously, you have uncertainty, but you are able to generate information in real time after a number of days that is pretty limited with rest. Well, that is much more advantageous than what is the state of the art at the moment for these systems. And so this is why this is happening. This is happening because the system is complex, because the airport and the international travel patterns are made by hub and spoke architecture. So you have the big airports and the small airport, etc. If we would live in a flat world in which airports are only like on a chessboard with 4 connections, this would be impossible. We would have to put gates, sentinels all over the places. The fact that we have this complex structure gives us an advantage that we can use to create a better sentinel system. To do that, we need infrastructure. Obviously, if we want to do this on a long term, the community needs to have infrastructure. And most important, and I will close here, is that we need to overcome a little bit what is the academic model that we have been working so far, in which generally you had the single teamwork. We were getting the data, sitting on the data until our elite publication is done, these kind of things. And get into something that is more collaborative is especially dependable. So there must be a readiness in the various teams that are able to contribute in real time to these things. And this is what we are trying with the Center for Disease Control and an initiative that is called InsightNet, that is basically aimed at building a kind of national weather system for epidemics. There are about a dozen centers, and our center is called Epistorm, and here you find a lot of information also on what I've shown today. And I think really this is possibly one of the initiatives that can bring us to a different posture when we will face the next pandemic. I think I can stop here. Thank you very much for your attention.